Hello and welcome to this exam preparation video on forces, describing motion along a line and Newton's laws. This is for GCSE Physics and Combined Physics, and don't forget to like and subscribe. In the journey from A to B, the arrow shows that a constant direction was taken. As the direction doesn't change, this can be described as a vector called displacement, units meters. It must have a direction. The wiggling line keeps changing direction, so this is a scalar called distance, units meters. Velocity and speed are similar, but velocity is a vector and so is in a straight line. Speed is a scalar, so does not have to be in one direction. Both are measured in meters per second. An example, the moon orbits the Earth at constant speed but not at constant velocity. This is because velocity is a vector, has direction and magnitude, so every time the moon changes direction, it is changing its velocity. Speed is a scalar, only magnitude, so it doesn't matter that the direction is changing, the speed remains the same. If something is changing its velocity, it must be accelerating, because that's what changing velocity is. If something is accelerating, then there must be a force making this happen. This force is gravity pulling the moon around in an arc. Gravity is acting as the centripetal force. This is a force which causes objects to move in a circle. For an object moving at a constant speed, to calculate the distance travelled in a specific time, use the following equation. Distance equals speed times time, or s equals v times t. Units, distance s, are the metre, speed v, units in the metres per second, and time t, units are seconds. If the object is in non-uniform motion, so the speed is changing, the average speed is needed. This can be calculated by using s equals vt if you use the total distance and the total time. However, if you're given the initial and final speeds, you can use the following. Average speed equals initial speed plus final speed divided by 2. There are some typical speeds that you need to learn. Walking 1.5 metres per second, running 3 metres per second, cycling 6 metres per second. A car travels at 25 metres per second, a train typically 55 metres per second, and a plane 250 metres per second. You also need to know that the speed of sound varies depending on what it's travelling through, so it's faster in a solid, for example. But the typical speed in air is 330 metres per second. If an object moves along a straight line, the distance travelled can be represented by a distance-time graph. The gradient of the graph gives the speed of the object. Speed equals the change in distance divided by the change in time. So in our first graph here, the purple line, we can read off our total distance and our total time. That gives us 80 divided by 2.8, so we have a gradient, our speed, of 28.6 metres per second. Then if we look at our second line in orange, if we read the total distance and total time, that gives us 40 divided by 6, which gives us a speed of 6.7 metres per second. So as you can see, the steeper the gradient, the higher the speed. There are some typical shapes of distance-time graphs that tell us certain things about the object. So a flat horizontal line tells us that the object is stationary. The diagonal line shows us that it's a constant velocity. If you've got a curve with a decreasing gradient, that shows that our object is decelerating. And if you have a curve with an increasing gradient, that shows that our object is accelerating, getting faster. Distance-time graphs can show acceleration or deceleration if the line is curved. If the gradient is increasing, getting steeper, the object is accelerating. If the gradient is decreasing, the object is getting slower. Taking a tangent to the curve allows you to find the speed of the accelerating object at that point in time. So here we have our distance-time graph, and on it is a curve, and this curve has got a decreasing gradient, showing that our object is decelerating. To find the speed at 3 seconds, draw a line on the graph at the point where the line of best fit, our curve, crosses the 3-second line. Use a ruler for this. The tangent should only touch the line of best fit at that one point, and the line of best fit should fall away evenly on both sides of the tangent. Then you find the gradient of the tangent by finding the difference in the distance and the difference in the time, and that gives us 80 minus 26 over 6 minus 0, which gives us a gradient, our speed at 3 seconds of 9 meters per second. Acceleration is the rate of change of velocity of an object. It is how much the velocity increases or decreases every second. It can be calculated using the following equation. A equals delta V on t, or acceleration equals change in velocity divided by time taken. Units: acceleration A is the meter per second squared. Change in velocity, delta V, the units are the meter per second. Time taken, t, the units are seconds. Deceleration is calculated using the same equation as acceleration, speeding up, and deceleration, slowing down, are the same thing. Deceleration is also the change in velocity divided by the time taken. Questions in the exam often say to rest or at rest. When something is at rest, it's not moving, so has zero velocity. When an object is moving and slows to rest, it has come to a complete stop, so zero velocity. Acceleration can also be calculated from the gradient of a velocity time graph. Here is our velocity time graph. We have velocity on the y-axis and time on the x-axis. Our purple line here, if we take our gradient of this, so our change in velocity is 0 to 80, so 80, and our change in time is 0 to 4.6, so 4.6 is our change. So 80 divided by 4.6 equals 17.4 meters per second squared. If we look at our orange line here and we do the same thing, we get our change in velocity, which is 28, divided by our time, which is 6, and that equals 4.7 meters per second squared. And as you can see, the steeper the gradient, the greater the acceleration. So the gradient of a velocity time graph can tell you something about the acceleration of an object. At the start here, we have a curve that's increasing in its gradient, which shows us increasing acceleration. Then the line goes straight, and that's constant acceleration is shown. Then we have a decreasing gradient, so we've got decreasing acceleration. Then we have a horizontal line, which shows us constant velocity. And then we have a diagonal line going straight down, and this shows us constant deceleration. In an exam, please remember to check, is it a velocity time graph or a distance time graph? Don't let that catch you out in your answer. Distance travelled can be calculated from the area under a velocity time graph. One method to do this is to split the area into familiar shapes, calculate the area of each shape, and then add up the results. So for this graph, it can be split into two triangles and a rectangle. Each of those areas can be calculated, so the first triangle is 50 times 2 divided by 2, and that gives us 50 metres. The rectangle is 50 times 4, which gives us 200 metres, and then the last triangle is 50 times 1 divided by 2, which gives us 25 metres. And we take all of those distances, add them together, and that gives us a total distance travelled of 275 metres. A second way to work out the distance travelled will be to work out the value for each square, count the number of squares, and then multiply the value by the number of squares. So using the count the squares method, 1 square equals 10 metres. Count up the number of squares, there are roughly 27 squares. Multiply that by 10, and that will give us an answer of 270 metres, which is approximately correct. The following equation looks complicated, but can be made a lot easier to rearrange if you substitute in the values that you've been given first. This is v squared minus u squared equals 2as, or final velocity squared minus initial velocity squared equals 2 times acceleration times the distance. You can only use this equation if the acceleration is constant. To use the equation, write it down, then substitute the numbers and simplify any maths. Rearrange to make the unknown the subject. Answer, use a calculator, it's faster, and then the units, there might be a bonus point for the unit. So here's an example question. A car travelling at 25 metres per second slows down. It does this under uniform deceleration of 2.0 metres per second squared. What will its velocity be after it has travelled a distance of 100 metres? Take air resistance to be negligible. So we write down our equation, v squared minus u squared equals 2as, and then we substitute in our numbers. So v squared minus 25 squared equals 2 times minus 2.0 times 100. And it's minus 2.0 because we're slowing down, it's decelerating. Simplifying some of the maths gives us minus 400. So we now have v squared minus 25 squared equals minus 400. Rearrange that to make our unknown the subject. So v squared equals minus 400 plus 25 squared. And that gives us v squared equals 225. Then we need to square root so we can get v as our answer. So the square root of 225 gives us 15 meters per second. An object falling freely through a fluid, liquid or gas, will accelerate due to the force of gravity. Acceleration due to gravity near the Earth's surface is about 9.8 meters per second squared. As the object falls, other forces oppose this movement, and eventually the resultant force will be zero. As the ball enters the fluid, the only thing acting on it is its weight. The resultant force is downwards, so it accelerates downwards. As it accelerates through the fluid causes drag on the ball. As the ball continues to accelerate through the fluid, the drag force increases and the ball's acceleration is less. Eventually, the drag force is as big as the weight. The resultant force is zero. The ball travels at a constant velocity until it reaches the bottom. This constant velocity is called terminal velocity. The object will remain at this velocity until another force acts on it. You need to be able to draw and interpret velocity time graphs for an object moving through a fluid that reaches terminal velocity. You also need to know about the forces involved and how they change the motion of the object. When a skydiver jumps out of a plane, the resultant force is downwards as the only force acting on them is gravity, which gives them weight. This causes an acceleration. As they accelerate, they experience air resistance. This causes a force in the upwards direction. As this decreases the resultant force, the acceleration also decreases. Eventually, the upwards force balances the downwards force and the skydiver stops accelerating. They now fall at a constant velocity. This is their terminal velocity. This is Newton's first law. An object will remain at rest or at constant velocity unless acted on by an external force. So when the resultant force is zero, an object will remain at rest. Or, when the resultant force is zero, an object will remain at constant velocity. If the resultant force is not zero, a resultant force causes an acceleration in the direction of the resultant force. The object gets faster. This tendency of objects to continue in their state of rest or uniform motion is called inertia. Newton's second law. Acceleration of an object is directly proportional to the resultant force and inversely proportional to the mass, which means if you double the force but keep the mass the same, the acceleration is doubled. If you double the mass but keep the force the same, the acceleration is halved. This can be summed up as F equals ma, or resultant force equals the mass times the acceleration. The units, resultant force F, is in newtons, the mass m is in kilograms, acceleration a is in meters per second squared. Inertial mass is the ratio of the force over the mass and can be calculated by rearranging the above equation to m equals F on a, or mass equals force divided by acceleration. Inertial mass is a measure of how difficult it is to change the velocity of an object. The bigger the inertial mass, the more difficult it is. Newton's third law. If body A acts on body B, then body B will exert an equal and opposite force on body A. For example, the earth pulls me down, but I pull the earth up by an equal and opposite amount. The cup pushes down on the table pushes up on the cup with an equal and opposite force. And that's all for this video. Thank you so much for listening.